Hello, welcome to this video. In this video, let us talk about dual cycle and we will also derive A standard efficiency for a dual cycle. Remember when we were talking about diesel cycle engine, we said that the heat is added at constant pressure. Now, how did we assume that? We assume that 0 to 1 as a suction stroke. Meantime, we can also write PV and TS diagram here. Our PV diagram is sufficient for now. If we recall, this is what we had done. In PV diagram, we said that the suction stroke happens like a constant pressure 1. So, this we named it as 0 to 1. So, this is what is 0 to 1, that is suction stroke where piston is coming downward and the only air is taken in during the suction stroke and inlet valve is open. And then the compression takes place, that we named it as reversible adiabatic compression, and that will be 1 to 2. Then we said since the temperature of the air at the end of compression stroke is so high that it would have reached auto ignition temperature, and because of which the moment we inject the fuel, it undergoes combustion and it starts expanding in the cylinder and pushes the piston downward. So, it will be like heat is added at constant pressure. This is what we had assumed, and then we said that there will be an expansion further, and then this is 2 to 3, then 3 to 4 is expansion further, that is 2 to 3 will be somewhere here to here, then 3 to 4 is from here to here. Okay. Then 4 to 1 is that during at the end of this expansion stroke, we will have that expansion valve or exhaust valve opened. So, the moment exhaust valve is open, most of the heat is ejected. So, it can be assumed as constant volume. Then remaining combustion products is pushed by piston. So, piston during the exhaust stroke. So, that can be modeled as 1 to 0. So, this will be 4 to 1 is here only happening at constant volume, then 1 to 0 will be like again constant pressure. So, this will cancel out. So, we will end up with only this much. This is what we had discussed in our diesel cycle, alright. So, this will be our 1, 2, 3, 4 and back to 1. But in reality, that we cannot assume that this will occur at constant pressure. The actual cycle will be close to dual cycle, which we call it as. That means, we can say that the moment we inject the fuel, there is some part of the fuel which ignites at constant volume. So, it can be modeled as some portion of this will be added at constant volume and remaining portion at constant pressure. So, that gives us what we call it as dual cycle. So, the heat is added at constant volume at some portion and constant pressure at some portion. Now, let us write PV and TS diagram for this correctly. So, I will just modify this. So, we are assuming that heat added in actual diesel cycle will be modeled close to dual cycle. In reality, it will be close to dual cycle. So, let us write PV as well as TS diagram. Let us write PV and TS diagram. Okay. So, we will start from compression only. So, 1 to 2 is reversible adiabatic compression. Then we will have 2 to 3 constant volume heat addition. Then 3 to 4 there is some portion which is constant pressure heat addition. Then there will be reversible adiabatic expansion. So, that is 4 to 5. Then again we will have 5 to 1 where heat is rejected at constant volume. So, this is reversible adiabatic compression, PV power gamma is equal to constant. So, this is where heat is added, Q supplied. So, that is volume constant. Now, heat is again added here. So, that is pressure constant, and 4 to 5 is reversible adiabatic expansion. Then 5 to 1 is volume constant heat rejection. So, volume constant heat is rejected here. So, heat is supplied during 2 to 3 as well as 3 to 4, which is at constant volume as well as constant pressure. So, This can be written in TS diagram as well. Now, TS diagram can be started from 1 to 2 is reversible adiabatic or isentropic, both are same. Isentropic means entropy constant. In a TS plot, it will be a vertical line. Then 2 to 3 would look like constant volume here, and again 3 to 4 would look like this, that is pressure constant. So, pressure constant will also be quite similar in TS diagram, pressure and volume constant. So, 3 to 4, then 4 to 5 is reversible adiabatic again. So, 4 to 5, then 5 to 1, 5 to 1. So, this will be again volume constant. Okay. So, this will be the cycle. We can again write here heat is supplied in two portions here. One is QS1 here, or and also here it is QS2. Then heat is rejected here in 5 to 1. So, we can name these processes, process 1 to 2, reversible adiabatic, compression, then 2 to 3 constant volume heat addition, then 3 to 4 constant pressure heat addition, then 4 to 5 again reversible adiabatic expansion, and then 5 to 1 is constant volume heat rejection. Okay, that completes the cycle. Now, let us derive A standard efficiency. So, we can start from efficiency is equal to, now we know that efficiency is given by work net divided by heat supplied, output by input. Then work can be rewritten from first law of thermodynamics, Qs minus Qr by Qs. So, this can be further written as 1 minus Qr by Qs. Now, we know from first law that Qr can be written as Cv, that is Cv for unit mass, or even if you write mCv, it is okay, it will be cancelled out mass. So, Cv heat rejection is happening between 5 and 1, and I already have used negative sign. So, I will try to keep this thing positive. Again, I do not want to use negative here. So, highest minus lowest. So, Cv T5 minus T1, alright, divided by heat is supplied in two stages actually. So, one is at constant volume and at constant pressure. So, at constant volume we will have the equation Cv T3 minus T2. See, this portion is constant volume. So, Cv dt Cv T3 minus T2 plus this portion 3 to 4 can be Cp constant pressure, therefore, Cp T4 minus T3. This can be further simplified with 1 minus Cv cancels out. So, this can be T5 minus T1 divided by T3 minus T2, but here it will be Cp by Cv. So, this can be taken here in the denominator. So, Cp by Cv. So, that will be gamma into T4 minus T3. So, this is our efficiency equation. I will call this as equation 1. So, we will come back to this equation 1 such that we will have to solve this equation where we will try to eliminate the temperatures and try to get it in terms of either compression ratio or explosion ratio, alright, or cutoff ratio. Now, if we look at this expression, we can see that there are two terms in terms of T3. So, maybe if we want to cancel out this temperature, our idea is to represent all the temperature in terms of T3. So, idea is, if at all we want to remember this equation derivation, represent all temperatures in terms of T3. So, that is what we will try to do. Now, let us start with process 1 to 2. Now, what is process 1 to 2? So, process 1 to 2 is P1 V1 power gamma. So, that is PV power gamma is equal to constant V2 power gamma. Now, we know that we can eliminate pressure. Already we are trying to do what? Temperature in terms of compression ratio. So, I will eliminate pressure. So, PV is equal to MRT I will use. In place of pressure, I can use MRT by V. Alright. In place of pressure, MR gets cancelled out. So, T1 by V1, V1 power gamma is equal to T2 by V2, V2 power gamma. Okay. So, that will be T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. Okay. So, I will write T1 is equal to T2 and this can be V2 by V1 which will be 1 by R and we have gamma minus 1. So, T1 is equal to, so therefore, we can write from here T1 is equal to T2 by R power gamma minus 1. So, I have represented T1 in terms of R power gamma, I mean T1 in terms of T2, but we were supposed to write it in terms of T3. So, once we write T2 in terms of T3, maybe we will replace it. So, I will call this as equation 2, we will come back to this equation little later. Now, let us go to process 2 to 3. Now, what is process 2 to 3? Now, process 2 to 3. Now, process 2 to 3, process 2 to 3 is constant volume heat addition, alright, volume constant. Now, what is volume constant? PV is equal to MRT, I will start. So, P, I will take this temperature to the left is equal to MR by V. For a closed system, we know that mass is constant, R is constant, and we are talking about a process where volume is also constant. So, whole right side is constant. So, P by T constant for 2 to 3. That means P2 by T2 is equal to P3 by T3. That is what we mean by P by T is equal to constant for process 2 to 3. Now, we can write that P3 by P2, I am just rearranging, P2 I will send it to this side, P3 by P2 is equal to T3 by T2. Now, if you look at here, this pressure ratio during which there is an explosion, that is constant volume heat addition is happening. So, let us call this as beta, which is pressure ratio during this explosion. Let us call this as explosion ratio. So, we can write this T2 in terms of explosion ratio. That means T2 can be written as T3 by beta. T2 can be written as T3 by beta. So, now we have written T2 also in terms of T3. Now, let us call this as equation 3, equation 3. Now, we can write therefore, now consider equation 2. Consider equation 2. What were we supposed to write? We were supposed to write T1 also in terms of T3. So, T1 is equal to T2 in place of T2, T2 is T3 by beta and R power gamma minus 1 is there. So, I can rewrite my equation 2 such that I will write T1 in terms of T3. Now, we have written T1 in terms of T3 and T2 also in terms of T3. Now, let us consider process 3 to 4. Now, consider process 3 to 4. Now, what is process 3 to 4? Process 3 to 4 is constant pressure. So, process 3 to 4 is pressure constant process. Alright. Now, for pressure constant process, I will start with same PV is equal to MRT. Now, for PV is equal to MRT, I will send this constant to the right side. So, I will take this temperature to left side. I will have MR by P. So, therefore, now M is constant for closed system, R is constant, and we are talking about a process where pressure is constant. So, the whole right side is constant. So, V by T is equal to constant for constant pressure process. So, therefore, V3 by T3 is equal to V4 by T4. So, I am trying to write T4 in terms of T3. So, T4 I will take it to the left side. So, T3 V4 by V3, alright. Now, what is this V4 by V3? If you look at this, V4 by V3 is cutoff ratio rho. So, V4 by V3 is cutoff ratio rho, alright, that we have discussed. So, V4 by V3 is cutoff ratio rho. So, T4 is equal to T3 times of rho, where rho is cutoff ratio, alright. So, therefore, we have got T4 in terms of T3. So, T4 is equal to T3 rho, alright. So, this also we have got. Now, I think we can consider to write T5 in terms of T3, then we are done. Let us call this as equation. Let us call this as equation. So, this was our fourth equation, equation 4. Therefore, now this equation will be equation 5. So, equation 5. Okay. Now, let us go to process. Next process is 4 to 5, all right, 4 to 5. Now, what is 4 to 5? Now, 4 to 5 is P4 V4 power gamma is equal to P5 V5 power gamma. So, what is it? We want to rewrite pressure in terms of temperature. So, MRT by V, and we know that T4 by V4 power gamma is equal to T5 by V5 power gamma. So, that will be T4 V4 power gamma minus 1 is equal to T5 V5 power gamma minus 1, alright. So, therefore, T5 can be written as T4 V4 by V5 whole power gamma minus 1, and we know that T4 is already written in terms of T3. I will replace it because we know that T4 is equal to T3 rho, alright, and this will be V4 by V5. Now, if you look at this, now V4 and V5 is neither compression ratio nor cutoff ratio or explosion ratio. So, V4 by V5 has to be either written in terms of cutoff and compression ratio, that we will have to take care. So, what we will do, we will try to divide and multiply by V2, alright. So, that is within the bracket, alright. So, T5 is equal to, now what I will do, so without changing the meaning of the equation, I am just rewriting T5 is equal to T3 rho, and inside this bracket V4 by V5 is there only, I am multiplying and dividing it by V2, alright. Now, what will happen? What is V4 by V2? Let us check. V4 by V2, V4 by V2 is nothing but V4 by V3, because V2 is equal to V3. So, because V4 is equal to V3, V2 is equal to V3, V2 is equal to V3, because V2 is equal to V3, we can write V4 by V3 as rho. Now, you see here, now V4 by V2 is rho. Now, we have T3, rho is outside, and this V4 by V3 is rho, alright. Now, what about this? V2 by V5? Let us check what is V2 by V5. Now, V2 by V5, this portion, alright, this much. So, V2 is here and V5 is here. Now, V2 is nothing but V5 is nothing but V1, alright. So, it is nothing but V1 by V2 reciprocal, alright. So, V2 by V5, where V5 is equal to V1, because V5 is equal to V1. Now, what is V1 by V2? Compression ratio, V2 by V1 is 1 by R, okay. Now, this will be rho by R whole power gamma minus 1. So, now what we will have? We wrote T5 also in terms of T3. Now, we can further simplify this. T5 is equal to T3 rho power gamma rho power minus 1. I am just splitting this term, and this we have R power gamma minus 1. This rho and this is rho power plus 1, and this cancels out. All we have will be T5 is equal to T3 rho power gamma divided by R power gamma minus 1. Okay. So, this is also written in terms of T3. Okay. Now, T5 is also written in terms of T3. Now, what we have done is we have written all the equations, that is temperatures in terms of T3. So, now let us call this as equation 6. Let us call this as equation 6. Okay. Equation 6. Okay. So, substitute all temperatures in terms of T3 into equation 1. Now, I will go back here. Efficiency is equal to 1 minus now T5 in terms of T3. So, T5 is what? T3 rho power gamma divided by R power gamma minus 1. Alright. So, this is our T5. Now, what is T1 in terms of T3? I will come back here. T1 is written in terms of T3. So, T1 is T3 by beta into R power gamma minus 1. T3 by beta into R power gamma minus 1 divided by, now T3 I will keep it as it is, minus, what is T2 in terms of T3? T2 is T3 by beta. So, T2 is T3 by beta plus gamma into, what is T4 in terms of T3? T4 in terms of T3 is T3 rho. So, this is T3 rho minus T3. Now, the whole idea of this was to take out T3 common and cancel out from numerator and denominator. So, I will do that first. I can take T3 common here, and also I can take 1 by R power gamma minus 1 in the common in the numerator. So, all we will end up with is rho power gamma minus 1 by beta in the numerator. Alright. So, T3 is taken out, R power gamma minus 1 is taken out. So, in the numerator, this is what we will have. Now, in the denominator, again we will take T3 common here. So, we will have 1 minus 1 by beta plus gamma into, we have taken already T3 common, we will have rho minus 1. Okay. So, this T3 cancels out. Now, let us simplify this further. Efficiency is given by 1 minus, I can do this 1 minus 1 by R power gamma minus 1 into rho power gamma minus 1 by beta. Alright. Now, this can be further simplified, right? I mean, this can be like, this can be rho power gamma minus 1 whole divided by beta. So, this will be beta rho power gamma minus 1. So, I am just, if you divide this, it will be like beta cancels out without changing the meaning of it. Now, similarly, in the denominator, this can be written as beta minus 1 divided by beta. Okay. And if at all you want to do this for whole division, it can be beta gamma into rho minus 1. So, if you divide this whole, this will be the expression. If you try to cancel it out, it will be the same expression. Alright. Now, this beta can be cancelled out, and we can rewrite this equation 1 minus 1 by R power gamma minus 1 into beta rho power gamma minus 1 divided by beta minus 1 plus beta gamma into rho minus 1. So, this will be the expression for a dual cycle. Thank you.